This is a proof of concept prosthetic arm I built for a case competition. I felt it would be an intriguing piece of content to talk about this year. Some of the things I learned, how I built it, what are some of the functionalities of this arm that you're seeing. Well, this prototype caters to the upper limb amputee market, specifically transradial and transhumeral amputees. Well, what about the arm made it a case comp winner? Well, this arm was initially developed to challenge two issues in the upper limb prosthetic space. One was exorbitant costs associated with upper limb prosthetics, and two, the heavy dependency on myoelectric sensors. Myoelectric what? That's probably a question you have, right? Well, a myoelectric sensor is something that's used to detect muscle movements in the residual limb of an amputee and convert that into signals and basically get the arm to move. That's the high-level explanation of myoelectric sensors. Obviously, there are many complexities associated with the myoelectric sensor, but all that adds to the cost of the prosthetic arm, and that's probably for another video, but that's one of the reasons why the arm is really expensive. My solution was to use TOF sensors, or time of flight sensors. Well, they measure how distant the object is from itself by measuring the time taken for the wave pulse that's emitted from the sensor to the object. They're inexpensive, quite reliable, and work very well for this prosthetic arm. Now here's me asking a very important question. Alright, so what are some of the functionalities of the arm? Yes, to answer my own question, the first one would be individual finger movements. Well, although the little and the ring finger in my arm move together, you know, to replicate the nuances of the human hand. Well, if you look closely at the anatomy of a human hand, the nerves of the small and the ring finger are intertwined and therefore they move together. You can check that out with your own arm. Well, also I didn't have space to add another motor in my arm, so I think it kind of worked well. So it's like hitting two birds with one stone. So yeah. The next one is wrist rotation based on object position. Well, based on where the object is with respect to the palm, the sensors detect that and align the palm perpendicular to the object, so object tracking. And finally, opening and closing of the arm. Based on how far the object is from the palm, the fingers dynamically move to either grab or let go of the object. Talking about the structure of the arm, we have the fingers right at the top, just like a human finger. We have 3 phalanx for the prosthetic arm too. The palm, located right below the finger, hosts the 2 TOF sensors. We then have a wrist connector, the part that mounts the palm onto the wrist servo motor. Below that connector, the wrist cage elegantly sits, housing the wrist motor. And lastly, the heaviest part of the arm, the forearm, housing 4 servo motors. One for the thumb, one for the index finger, one for the middle finger, and the last one for the small and the ring finger. Well, the fingers move based on string tension. A string is wrapped around the horn of the servo motor and travels all the way up through to the tip of the finger. When the servo motor rotates, it pulls on the string and the finger coils. Alright, moving on. This is me trying to explain the circuitry of the arm. I hope you understand something, but take a listen anyway. Come on here, buddy. I'll show you something pretty cool. So what we have here is the back end of the circuit design of the entire prosthetic arm. In a nutshell, we have the Arduino Mega, which is a microcontroller here. It sends power to the sensors, about 5 volts, and also sends signals to the servo motor to move in certain positions. These are the servos. We have another one inside the wrist. Well, following that, to power these servo motors, we have a very powerful 6-volt battery. Is that right? Yeah, that's it. 2400 milliamp hour battery, a lot of power, a lot of current. We also have this really messy circuit board that comprises of all the usual suspects you find on a circuit board. Diodes, capacitors, wires, missing anything? Resistors, of course. And we also have this little fun push button. See that? Well, the reason we have this push button is to abort any gripping stance that the arm has. For example, let's say there was an object that was stuck in the arm of that and kind of clenched up. And was clenched up. Hitting this push button kind of open it up on the spot and kind of let go of anything that it was holding. Well, obviously, this does look really messy, so I do have a schematic diagram that could probably explain a lot better. It'd be a lot better for you too. This looks a lot better, doesn't it? This is the schematic diagram of the circuitry for the prosthetic arm. Well, the first thing that pops out right out of the screen would be the Arduino Mega, which is a microcontroller for this project, some might call it the computer. On the top right, we have the 2 sensors, the VL53LOX sensors, powered by the 5-volt pin from the Arduino board, and we have a common ground too. If you take a closer look at the sensors, you'll see an SCL and an SDA pin. This refers to the I2C bus. So the distance data that's recorded from these sensors is then sent to these pins, which are then in turn sent to the Arduino Mega. Well, they kind of the sensors talk to each other using the I2C protocol, and that's how we roll. Well, the Arduino has some code that I written for it, and using that code, this information is sent to pin 9, 7, 6, 5, and 4. Pin 9 refers to the wrist servo motor. The 7, 6, 5, and 4 pins refer to the finger servos. If you look at the bottom right, those are the servo motors. All the servos are powered by an external source, which is the 6-volt battery that I'd shown you previously, the nickel metal hydride battery by 2400 milliamp hour battery. Yeah, all in all, this is what the circuitry looks like. It's not too shabby, and yeah, that's it. That being said, a question might arise. How do you let go of an object once the arm latches onto it? Well, you can't just yank it out or snatch it right off the arm. That's a very ungraceful way of letting go of an object, isn't it? So to address that one specific issue, I thought of buying a myoelectric sensor just for that one specific task. So I bought the MyoWare 2.0 sensor from Advancer Technologies, but unfortunately the stuff that they were selling was faulty, and all the products they had in that line, all the MyoWare 2.0 sensors were faulty for some reason. So I used a push button instead as an alternative. Oh yeah, I forgot to mention, we also have a cover. If you see this, we have 2 holes for the screws that go right on here. If you see that, and we just simply place it right on top, and we screw the bottom part, 1 and 2. See that? So all in all, it kind of looks like this. And finally, we get to the code. So in essence, this is how the code of the prosthetic arm works. Let's say we're looking at the top view of the hand. We have the 2 sensors positioned in front of the palm. This would be the scanning spectrum of sensor 1 and sensor 2. Now I believe for the VL53LOX sensor, it stretches out to about 2 meters at best. So if an object fell within the 2 meter proximity of either one of these 2 sensors, the sensors would be able to detect it accurately. So in our case, let's say we have an object in front of sensor 1, slightly deviated to the left side of the center of sensor 1. And just like every other time, sensor 1 would accurately find the distance of that object from itself. But in sensor 2's case, it would be slightly different, because the sensor would keep looking out for an object till it either hit that 2 meter limit or found an object slightly before that. Obviously, in this case, sensor 1's distance data would be shorter than sensor 2's distance data, and thus we know for a fact that the object will be positioned on the left side of the hand, and therefore the code simply instructs the wrist servo motor to move to the left side. Therefore, it would be positioned something like this, to a point where the object is center aligned to the sensor 1, between sensor 1 and sensor 2. Now, the distance should be roughly the same, I believe. I do have a 4mm cushion just in case, to avoid any unnecessary jittering action performed by the wrist to center align the object with respect to the hand. But apart from that, this is basically how it works. The sensor values keep updating every 50 milliseconds, so we get an accurate representation of where the object is with respect to the hand. So yeah, in essence, this is how the code works for the wrist. That being said, what if you had a scenario like this? Let's say there was an object in front of sensor 1, and there's also another object in front of sensor 2. How would the arm know what object to pick? Well, my assumption here would be that if an amputee wanted to hold on to something, they'd probably position the prosthetic arm closest to that object, right? So in this case, it would be the object in front of sensor 1. So the sensors basically calculate the distance between both the objects and then find the shortest distance between the 2 of them and then go after the closest object. So in this case, the object in front of sensor 1 would be the object the calculation would be done for. And finally, the opening and closing of the fingers. Well, that was relatively straightforward. As the object approached the 2 sensors, the hand would gradually close, and vice versa. As the object moved away from the 2 sensors, the hand would gradually open. I did this by hard-coding the values in. For example, let's say the object was 50 millimeters away from sensor 1 and sensor 2. Well, the wrist servo would shut off, and the finger servos would turn on, and would be positioned at a 100 degrees angle. Each servo motor is connected to a couple of strings, and each string was in turn connected to the tip of a finger. So at 100 degrees, the string would be pulled, and therefore would kind of pull the finger closer to the palm, therefore coiling it in. So that is basically how the fingers open and closed. Alright, thank you all for watching. Well, that's the end of this project, so yeah, that's basically what... Alright, thanks for watching the video. That's basically it. This is what the prosthetic... Well, that's basically the end of this project. I'd like to thank you all for watching this video. I have a couple of extra clips if you'd like to see about how this project came to fruition, right from the start of the design to what it looks like right now. Until then, thank you once again for watching. I'll see you all next year.
You have 5 fingers, 1 wrist. You have 4 motors.
There are 4 motors and a wrist and a motor inside, see that?
Oh.
Yeah, that's kind of the other one.
So one finger doesn't.
have a motor?
No, so what I'm going to do is I'll have one servo for this stop, another servo for this, another servo for this, and let's go for another high five, buddy.
Good job.
Let's go for a handshake too.
Good job. Good job.
Well done. Investment. Thank you very much. Thank you. That's it. Thank you. Raj, come here, buddy. Let's go for a handshake.
A hug.
Oh, come on, bro.
Oh,
Congrats, buddy. Congrats.
Thank you.
Look at these 2 beautiful brothers.
That's all I can do.
You got a high five handshake.
High five handshake. The prosthetic arm. Let's go.
Yay.